Hello? Hello? ይሰማችኋል? እንትኑ ስልኬ ከስልኬ ነበረ ኢንተርኔቱ የምጠቀመው ስልኬ ባትሪ ዘጋብኝና ለዛ ነው።
Okay.
ስለዚህ let's start again.
Yes.
I'm sorry for that. So is it visible there?
Yes.
Yeah, it's clear.
Okay, so what we are talking here is about the basic fundamental concept of rocket propulsion. So on the fundamental concept, what we are going to see is the component of rocket motor. So these are some basic components. So how it works, that is our question. How the rocket works, how the rocket move from the ground to the required destination. So it is just because of the momentum, the rate of momentum that produced from the propulsive unit. So thrust is in the forward direction and the momentum, the rate of momentum in opposite direction. So due to that, the rocket will move. So the rate of momentum, which is the mass of ejected propellant, which is coming through the rocket nozzle, times the velocity of ejection. Okay, so this velocity is different from the velocity of the vehicle itself. So in addition to the forward force, in addition to other drag forces and so on, weight also have its own contribution on the near Earth's atmosphere. If the flight is away from the Earth's atmosphere, then we have no such issue. But in the low altitude, there is gravitational force, there is frictional force due to air resistance, and so on. So that is one of. So this is the direction of velocity of rocket, and this is the direction of the ejected mass, okay, which comes out through the rear part of the rocket. So this is the eject velocity, you see. So there is pressure force, there is an area of the exit area, pressure area. So those things are there. So the mass, eject mass, that is the amount of propellant consumed within a moment, is related with the pressure, the gas constant R, and the temperature times velocity of eject and times area. So this is the relation for m dot. So this P RT is related with the velocity. Standard atmospheric pressure temperature conditions. So P over RT of the ejected matter times velocity of eject times exit area or eject area. This area eject means exit area of the rocket. Okay. So the thrust force T is equals to m dot v. M dot v means the mass flow rate of the amount of propellant consumed within a second. Okay, so mv plus p minus that this p eject means p exit minus p infinity means it is just the atmospheric pressure. P exit minus P atmosphere times area of eject. So this area of eject is area of exit. So this part of thrust is known as momentum thrust. This we call the first term in thrust equation is called momentum thrust. And the second term, which is P eject minus P, hello? Hello? ይሰማችኋል?
ሄሎ እኛ ነው ዶክተር? አዎ ይሰማል።
የሆነ ድምጽ እየመጣ ስለሆነ Okay, so this first term is called the momentum thrust. And the second term is known as pressure thrust. So we have kind of terms that optimum expansion of a nozzle, over-expanded nozzle, under-expanded nozzle, optimum expanded nozzle condition because of this term only, because of the pressure term. If the pressure term is 0, then we have left only the momentum term. This is called momentum thrust, we call. And this is of the pressure thrust. Okay, so in optimum condition, pressure exit is equal to pressure atmosphere. Then it becomes the first term remains as a thrust. That is called optimum expansion of the nozzle. If this part exit pressure is greater than atmospheric pressure, then it adds on the thrust. It gives more thrust for this thing. So it is called the overexpanded condition. And if it is this, if eject pressure less than atmospheric pressure, it subtracts our thrust from the momentum thrust, so that it is under expanded nozzle condition. So those three conditions are there. So what is overexpanded, what is underexpanded, and what is optimally expanded nozzle. So we have to check that. So this is the mass flow rate, m dot. This is the direction of velocity, and this is the thrust force, which is taking a vehicle in forward direction, and this is the drag force. So these are some of the fundamental forces which are acting on on a moving vehicle. Okay, so what's that? This, yeah. So these are the four forces. One of the force is thrust force. The second is drag force. Another is the weight of an object, and also we have another aerodynamic forces, or there may be there is no lift condition here. It is lift is from the wings. So these are the fundamental forces in the case of rocket: thrust, drag, weight. Okay. Actually, in any moving vehicle, including airplane, the forces are four. The four basic forces acting on flying objects are thrust, drag, weight, and lift. Okay, so the weight is mostly from the aerodynamic surface, the lift, I mean. So P represents rocket thrust, D represents rocket dynamic drag, and VR is the velocity of rocket. So M dot is the mass flow rate of ejected matter, and MR is the mass of the rocket. So the total mass of rocket is considered MR. Okay, so these are some of the force. So we apply conservation of mass principle in order to solve this rocket problem. Conservation of mass should be maintained. So what kind of internet? So we have external environment, we have internal environment here. As you see, this is the system boundary. This is just, you can consider the rocket system as a system. So you may have some kind of system boundary. We have external environment here. Okay, we have also internal environment. Okay, so in a closed system, there is, you know, what is closed system and what is open system. So at the boundary, the energy considered zero. At the outside of the system, U is given as zero, And at the boundary, exactly at the boundary, u is equals to u of a. So that is the, so it is within the kind of thermodynamic system. You know how we can define thermodynamic system. Okay, so pressure node, pressure one, u at exit, u area at exit. There are also propellants here. Velocity of rocket is there. Okay, surface area of the given system is here of the rocket, and another area is area 2 is there. Atmospheric condition P naught is there at the time t greater than 0. So this is kind of system definition. So what we are saying, momentum conservation or mass conservation. On that, rocket mass times acceleration gives us thrust minus drag minus gravity effect. Okay, thrust is the only force which gives forward motion, so that others are the denying motions. Drag, the dynamic drag also denies the motion. The gravity also accelerating an object in the opposite direction, downward, so that the mass, the rocket mass times the rocket acceleration, which is equal to thrust minus drag minus gravity effect. So this is a simple expression for the rocket. So the total mechanical impulse, or what we call total change in momentum. This is not momentum, but momentum generated by applied force T. Our applied force is only the thrust force. Okay. So there is some terms which are not readable here. Anyways, yeah, we can see these points later. And our time is now, we have left only 4 minutes, so I have to restart this slide. Some kind of requirements to reach on an orbit. For a typical launch vehicle headed to an orbit, aerodynamic drag losses are in the area of 10 to 50 meter per second, 100 to 500 meter per second. This is the loss because of aerodynamic drag. Gravitational losses are larger, generally ranging from 700 to 1200 meter per second, depending on the shape of the trajectory to the orbit. So this loss should be considered while we are designing, because both of the gravity and drags are the opposing forces for the motion. So by far the largest term in the equation of the space velocity increment, actually we will see what is the velocity increment. That change in velocity of the vehicle is equals to specific impulse times ln of mass initial over mass final. Mass initial means the wet mass of the rocket, and the mass final is the mass remained after burning. Okay, so how we can define that? Let me write some term on that screen. Okay. Pointer PM. Okay. So change in V, change in U, I can say the velocity change of the rocket after encountering all the gravitational effect as well as the aerodynamic drag is equals to ISP, specific impulse, ISP times ln of the natural logarithms, ln of m final, no, m initial, m naught over m final. Why? Because m initial is greater than m final. M final. So this m initial, m naught is the initial mass of the overall mass of the given propellant, and M final is the final mass. After burning some amount of mass, what we have left is M final. So we can relate it. So the lowest altitude where stable orbit can maintain this at an altitude of 185 kilometers. That is the height where we can obtain a stable orbit. So this is the way how we can select flight orbit. So this requires an orbital velocity of approximately 7,777 meter per second, or 7.78 kilometer per second. So most orbital speed should be in range of 7.78 meter per second at least. And the escape velocity, as we have discussed previously, the escape velocity of rocket is at least 11.2 kilometer, okay, or 11,200 meter per second. But the orbital velocity of a vehicle, that to maintain the vehicle within the given orbit, should be 7.78 kilometer per second. That is the requirement to reach an appropriate orbit. Launching time requirement. So launching time also is one of the paramount important. As the launching time delay, there may be a disastrous kind of failure may happen. So an appropriate launching moments are also be designed. So to reach this velocity, the velocity to launch is at the moment launching, it should be having kind of escape velocity. So to reach this velocity from space center, the rocket requires an ideal velocity increment. This is velocity increment. It is not just a velocity, but the velocity